thermodynamic forces are the gradients of affinity. So essentially, delta beta, which is the difference in between beta left, beta right, or delta beta mu, which is the difference between beta mu left and beta mu right. Sorry, I heard the noise. Can you guys hear me? Is everything okay?
It's okay.
Okay. Sorry, I just heard a noise. I thought maybe my connection dropped. Okay, sorry. Moving on. Okay, so essentially, in linear response, so if the gradients are small, if these deltas are small, then the fluxes will be linear in the gradients. And this is the starting point for Onsager's classical theory of transport. So you can have a flux of energy, you can have a flux of particle, but they will depend on the gradients of beta and the gradients of beta mu. The coefficients that appear in front at linear response are called the Onsager coefficients, and they form this Onsager matrix. So, for example, these two coefficients, LEE and LNN, they're related to the famous Fick's law of diffusion and Fourier's law of heat conduction. So LEE, for instance, is how heat flows due to a gradient of temperature. So it's Fourier's law. And LNN is how particle flows due to a gradient of concentration, which is Fick's law. Now, when I forgot to mention this, when I talk about particles, I can mean both like the flow of particles like in a chemical reaction, for example, or it can also mean just a flow of charges like in a conductor, like flow of electrons. So Fick's law would be Ohm's law in that case. What is very interesting about Onsager's theory is the prediction of these cross coefficients, which are less intuitive. So LNE, this guy, it represents how a gradient of temperature generates a flow of particles or electrons. So this is called the Seebeck effect, and it's the basis for thermocouples. Thermocouples, they measure temperature by measuring current, and that's exactly the basic working principle, is that a gradient of temperature generates a flow of particles. And the other one, LEN, is called the Peltier effect, and it's associated to how a gradient of concentration generates a heat flow. Now, this is used, every laptop has a thermoelectric plate, which is used to cool it and stop the processor from overheating. And the Peltier effect is really the basis for this kind of application. And we can also characterize the thermodynamics of this process and the second law of thermodynamics by constructing what's called the entropy production rate, the rate at which entropy is irreversibly produced. Now, the entropy production rate from thermodynamics is given by a product of gradients versus current times currents. And so if we substitute Onsager's form, we get a quadratic expression in the gradients. So we have the Onsager matrix here, L, and it's like a quadratic form in L. Now, Onsager's main result on this was actually twofold. I mean, what I said so far is not really Onsager's main contribution. His main contributions are these two effects. First, L is symmetric. So the Onsager matrix is symmetric, which means that the Seebeck coefficient and the Peltier coefficient are actually equal. And this is highly non-intuitive. I mean, it's not at all obvious that they should be, but they are. And secondly, L is positive semi-definite. So it forms the matrix L is a positive semi-definite matrix, which implies that the entropy production rate is positive. So this here, this inequality is an expression of the second law of thermodynamics. Okay, now, recently, there has been a lot of interest in extending these ideas, which are pretty much classical, into the quantum domain. Now, this is one absolutely beautiful experiment of playing with Onsager transport in ultra-cold Fermi gases. So what's done here is essentially you have a gas of fermions, which using lasers, they are split into two blobs. So you have a left blob and a right blob. And the blobs are prepared to have different particle numbers and also different temperatures. So by using a heating beam, they can heat up one of the blobs. Now at T equals 0, they lift here this constriction, separating the gas clouds, and they allow them to interact. So what's going to happen is that, the two systems, hot and cold, they are going to exchange particles and they're going to exchange heat. This is the experiment. For instance, here is the temperature of the two gases, and you can see that they're thermalizing. So hot is here, cold is here. As time moves on, both of them become just equal temperatures. And this is the flow of particles. So you can see that, initially there's a large flow of particles, and then eventually this stops. So the two systems also thermalize to have the same particles. So this is a very nice illustration of how we can take that Ansager idea and export it to a very, very microscopic and very quantum setting. Okay, but what I showed you so far concerns abelian charges. Abelian means that they commute. Energy, the Hamiltonian, and particle number are operators that commute at the quantum level. But there's nothing in quantum theory that forbids us to just studying the same problem with non-commuting charges. So we can imagine having similar kind of state of affinities times charges, but simply having charges that don't commute among each other. And this is what's called non-abelian charges. And states like this are nicknamed NATs, non-abelian thermal states. One very simple example is just a spin transport. If you're able to prepare your states such that you have Pauli matrices, not only Z, but also X and Y, then this would be a nice example of a non-abelian thermal state. Another example that I'm going to illustrate in a bit is radiation squeezing, which is a property that's widely used in quantum optics. Now, in last maybe 6 years, there has been a lot of interest in extending thermodynamics to non-abelian charges. So these are two very influential papers in the field, which appeared back to back. So you can see that they're published at the same date, which introduce many of these ideas about using multiple charges which don't necessarily commute with each other. And this very recent, just 4 months ago, is the first experimental demonstration of non-abelian transport. So what they did here was they have a spin chain, a one-dimensional spin chain with a Heisenberg Hamiltonian, but they prepared this chain in a way that it's split into 3 parts. So you have a left environment, a right environment, and a system in the middle. And you allow it to exchange not only sigma Z magnetization, but you allow it to transport sigma X and sigma Y magnetization. And here is a full tomography plot of all the spin components as a function of time. So time goes this way, and these are the spins. This is used, was produced using trapped ions, so that's why it's called ion here. And you can see the evolution of the magnetization. So each of the magnetization components, they evolve, and you see that the system is thermalizing, right? So it's evolving, and it's eventually, there's a homogenization process where the system eventually thermalizes. And this is also another plot from the same paper, just showing, I'm not going to go into the details of the plot, but just showing that the NATs that I was describing before, they are superior in describing this thermalization process than a canonical or grand canonical ensemble would be. Okay, so this is, I think it's a good motivation. Non-abelian transport is something that is within reach of modern quantum technologies, and there's loads of unexplored things to do and to try to understand. So now I'm going to discuss our take on the subject, how we approach the problem. So again, we have a condition, a scenario similar to what we had before, where we have 2 systems, left and right. But what we're going to assume from now on is that the interaction process, so the way that these 2 big systems interact, is actually by colliding small units. So you can imagine that this system is a gas, this system is a gas, and there are small collisions where a unit of the left system and a unit from the right system, they get together in the middle, they interact, and then they are scattered back to their original reservoirs. Each unit is prepared in a non-abelian thermal state. So the notation is a little bit like this. You have X here to denote A and B, and you have lambda X to denote the set of affinities of A and B. So the two of them are in general prepared with different affinities. And the interaction map is essentially a unitary operation. So you start with both units in a thermal state, in a product state, independent product states, and you apply unitary. Now, what happens is that the output state is just a correlated quantum state. So it's a rho AB prime. Prime means after the collision. And this is just to emphasize that they're correlated. Now, the first crucial question that we have to ask is, when does it make sense to talk about process? Because, I mean, up until this point, this unitary can be anything we want. This is too general. So when does it make sense to actually talk about transport? By transport, what I mean is something must leave one place and go to another place, right? That's what transport is supposed to mean. So what's the condition for whatever thing you're transporting to be conserved as you move from one place to another? Well, this condition can be shown. It's called strict charge conservation. You have to impose that whatever unitary you have, it will commute with the sum of the two charges for each pair of charges. It does not commute with the charges individually. So we do not want the unitary to commute with the left charge or the right charge, because that wouldn't give us anything interesting. We just want it to commute with the sum of the two charges. I'll show you examples in a bit. If this is true, if for whatever process we have, the unitary satisfies this, then charge is conserved, which means we can define a unique current operator, which is just the Heisenberg evolved charges. So it's the initial one, it's the final one, U dagger minus the initial one. And this is going to be equal to minus the same thing for the other side. So whatever leaves one system enters the other. That's the crucial hypothesis that you need to satisfy if you want to talk about transport. And then, of course, once you have a charge operator, you can define an average charge and move on from there. Okay, next, let's talk about entropy production. So how do we construct entropy production from this kind of process? There's a very nice way introduced in this paper and reviewed here to construct entropy production solely from quantum information theory. And essentially, it's given by this formula, which has three terms. The first term, this I prime, is called the mutual information, and it's a measure of correlations. S here is the von Neumann entropy. So I is essentially the amount of correlations that A and B develop during the collision. So initially, the two units were uncorrelated. They were in a product state, but then they are put to interact and they get correlated. Now, this correlation is part of the entropy production. And the other two terms are based on this object, which is called the quantum relative entropy. And it's a measure of distance. So essentially, the other two terms refer to the distance between the initial state of each unit and the final state. So rho A to rho A prime. And each of these three terms are non-negative, and so their sum is also non-negative, which is a manifestation of the second law. And what is particularly nice is that if we now substitute here the specific structure of rho A and rho B, so the fact that rho A and rho B are nets, then we get that the entropy production is just given by the familiar thermodynamic formula. So this is a very nice way to show that even for non-abelian charges, if we start with this information theoretic framework, we recover an entropy production that is given by a familiar thermodynamic formula. Okay, and now we're going to do linear response. So we're going to assume that system B has a set of affinities that I'm just going to call lambda, and system A has a set of affinities which are just a little bit off, so lambda plus delta lambda. And therefore, we can expand the currents just like we would do in Onsager theory as a series of coefficients, numbers, LKJ times the gradients. And these LKJ will be the Onsager matrix. Now, here's the first main result that I wanted to present. The result is that we find a way of computing the Onsager matrix, which takes into account the fact that they don't commute. It is given by this formula, which depends on a special object called the Y covariance. So a Y covariance, this cov Y, is a generalization of the notion of covariance to objects that don't commute. It's defined like this. So the Y covariance of A and B is a little bit like the covariance. You know, the covariance would be average of AB minus average A, average B. But the Y covariance has a Y in the middle here. So it's, instead of putting the row anywhere you want, you put row to the Y in the middle and row to the 1 minus I in the other side. And now if everything here commutes, then you can just take this guy and put it in here, and you just get a usual covariance. Otherwise, you get this generalization. And so essentially, the Onsager matrix is given by the Y covariance of the current operators. If the charges commute, then this whole formula simplifies and we just get a covariance. And this is the famous Kubo formula. In this particular scenario, this is just the Kubo formula, which essentially relates the Onsager matrix with equilibrium covariances. Otherwise, if the charges don't commute, then we get this generalization. So we have to take this into account. A particularly nice side comment about this is that the way we derive this result is based on concepts from quantum parameter estimation, which is we felt was kind of cool because we're using, you know, results from another area. And in particular, this idea of a symmetric logarithmic derivative, which is the operator solution of this equation. And so we can actually relate the Onsager matrix with correlations between currents and SLDs. So that was kind of cool. But this is just a technical remark. Okay. And now what is the consequence of this main result? Well, the most interesting one, in my opinion, concerns the entropy production. So from this, it follows that the entropy production is also given by a Y covariance of this operator D here, where this D is an operator which is just the gradients times the charges. And what is particularly nice about this result is that we can now split it into two terms. We can split it into a commuting part, which it would have the same form, but with commuting operators, minus this quantity I, which is a widely known quantity in information theory called the Wigner-Yanasi-Dyson skew information. And it's a quantifier of coherence, of quantum coherence. So this result essentially says that the entropy production is reduced with respect to the commuting case by a factor associated to this Wigner-Yanasi-Dyson skew information. So non-commutativity reduces the irreversible entropy production compared to a commuting case. And it does so because by a term that is associated to quantum coherence. So I think that's particularly cool. Another way of seeing this is we can also view the average entropy production as just the average of this operator D. And so if in the commuting case, we would get the fluctuation dissipation relation that, you know, the average is just 1/2 of the variance. This would be the classical, the famous fluctuation dissipation relation. But when they don't commute, this is broken and we actually get a violation of the so we break the fluctuation dissipation relation again by this factor I. So, you know, it's no longer the average is no longer the variance, but it's reduced with respect to the variance by a factor I. Okay, now let me go on to discuss the first application of this, which is the so-called thermosqueezing effects. So squeeze states are very widely used states in quantum optics. They have a lot of very powerful properties, and in particular, they are used for quantum sensors. So, for example, gravitational wave detectors, they use squeezing to improve the sensitivity. Now, a squeeze state is easy to understand thinking about a harmonic oscillator. The usual thermal state of a harmonic oscillator would be e to the minus beta h, where h is just, you know, p squared plus x squared for the harmonic oscillator. You can make this state squeezed if you add to it another term, which is proportional to p squared minus x squared. So this new term is called squeezing. Some people call it asymmetry, but maybe that's a controversial name, so it doesn't matter. And this state is now a squeeze state. So if you look at it in terms of phase space, position here and momentum here, then the vacuum of the harmonic oscillator is a blob, a thermal state is a bigger blob, and a squeeze state is a squeezed blob. So essentially you're squeezing within some direction. This would be a kind of squeezed thermal state. There has recently been a lot of interest in using squeezing for thermodynamics. These are just some of the papers that have appeared in the literature in the last few years. The basic idea is that you can actually use squeezing as a resource. So you can use squeezing to, for instance, build a thermal engine which has nice properties, such as, for instance, operating beyond the limit imposed by Carnot. This is a particularly nice paper. It's an experiment from 2014, where they create an engine which is operated with temperature and squeezing. So here's a thermodynamic cycle. You see there's like the strokes of the engine, and this is implemented in a nano beam. So it's essentially like a small vibrating membrane that you shine light on with whatever modulation you want, and you use this to mimic a bath, a squeezed bath. So essentially, as the cycle progresses, you have here the cycle time, we are changing it, they change the temperature. So you see, you heat up, cool down, heat up. This is like the cycle, but you also change the amount of squeezing. So you go from a symmetrical blob to a squeezed blob, which goes essentially up and down in a similar fashion. Oh, sorry, and I just forgot to mention, you know, one of the nice things that they do here is to show that this operates beyond Carnot limit. Okay, so now going back to squeezing, a nice feature about this squeeze state is that these operators, they satisfy SU11 algebra. So you actually have three charges. You have Hamiltonian, this A operator, and you can also have another one, which is the anti-commutator of X and P. And these satisfy a SU11 algebra. So they form a non-abelian group, hence the name, non-abelian transport, right? For simplicity, we're just going to focus on two of them, but we could also focus on all three. That would also be a possibility. And a very interesting question is, which kind of unitaries will satisfy strict energy preservation? Now, remember, I spoke about this a while ago, that not all kind of interactions would be good for non-abelian transport, because they will not necessarily conserve all the charges. Now, we actually show in this paper that for this kind of system, the only unitary, the only one which is quadratic, so Gaussian, and also conserves both charges, is one of this form. Essentially hopping with a specific kind of phase here. Okay, and now we can therefore build the usual Onsager theory, but for energy and squeezing. So we can build a Onsager coefficients for heat and for transport of squeezing. So we can have a Peltier effect, which is whenever a gradient of squeezing generates a flow of heat, and we can also have the Seebeck effect, which is which I kindly nicknamed the Squeebeck effect. Which is when a gradient of temperature generates a flow of asymmetry, or a flow of this A guy. Okay, these are just some illustrations of what happens. We can compute these things analytically. They will depend essentially on the Bose-Einstein distribution and bar, and on the degree of squeezing, mu here, which is like the chemical potential, and also on the interaction time g tau. We can define all kinds of standard thermoelectric quantities. So we can have a thermoconductance, conductance, and squeezing conductances. And we can also have dissipated heat. So it's quite interesting to look at the shape of the dissipated heat. What we get is that there is a usual thermal dissipation, which is associated to the heat flow. But quite nicely, there is a new term associated to Joule heating. So there is now an additional contribution to the dissipated heat, which is associated to squeezing. And these are just some examples of how the Onsager coefficients behave. Remember, I don't need to plot L21 because of Onsager's symmetry. L21 is the same as L12. So these are all the Onsager coefficients. Here is a function of the inverse temperature. So this is cold and here is hot. And this is a function of squeezing. So here is no squeezing and up here is a lot of squeezing. So this is pretty much how they depend. And more interesting is the entropy reduction. So remember, I discussed how the entropy production is the commuting entropy production minus a reduction factor associated to the Wegener-Yanasi-Dyson scale information. So we can define a ratio, which is essentially this last term divided by sigma, which is which represents how much the entropy production is reduced in comparison to the classical case. And this is a plot showing how it behaves. You see that at very cold temperatures, there is a very, very significant reduction, and at high temperatures, it's much less. And so this is the typical behavior of how the entropy production is changed due to quantum coherence. And this final plot for this example is just illustrating the Squeeback coefficient, or what's called also the thermal power, and the Squeezing-Peltier coefficient, and also how this is a plot of the thermal power. Okay, to illustrate it with another example, we can also consider spin S dynamics. So suppose we have a spin S with 2s plus 1 eigenstates of Sz, but suppose we consider nets which are of the form with Sz, but also a term corresponding to Sx, right? So now you can have, what this means is that you can have transport of Z magnetization, or you can have transport of X magnetization. And this is a very beautiful problem because X and Z, they don't commute because they are spin operators. But we do know that if the spin is very large, this shouldn't be too important because the spin commutation relations usually are not that important for large spins. They are relevant for small spins. Now, what kind of interaction do we need to use in order to satisfy strict energy conservation? Well, the natural choice, which works very well, is the Heisenberg interaction. So Heisenberg is fully isotropic, SA.SB. This will preserve all spin contributions. So here are some plots. What I'm showing you here is the entropy production and the Wegener-Yanasi-Dyson contribution. And I'm plotting this for different times, but as a function of S. So as a function of the spin size. And so what you see is that if the systems are big, so as you increase S, everything tends to increase usually, especially the entropy production. So more entropy is produced when you put large spins to interact. But the relative contribution of sigma and the I term becomes less relevant for large spins. So while if you are for like spin 1/2, the quantum contribution, so this I can be viewed as a quantum contribution, right? It's very relevant for small spins. As you go to large spins, it tends to be less relevant. Although there are very important oscillations. So if you look here, there are like some oscillations as a function of S. So for some spin sizes, you can still get very meaningful contributions from the quantum part. Okay, and then this leads us to another question, which is how do we measure these things? I mean, how do we actually go and measure non-Abelian, non-commuting charges? Well, the standard protocol that is used in thermodynamics to measure these things is called the two-point measurement. Essentially, the idea, the basic idea, and this is very, very deep in my opinion, is that thermodynamics always deals with transformations. When we say something like a heat current or a particle current, what is really meant is a change, is a transformation from initial to final, right? So in order to measure that, we need to do two measurements. We need to measure once, then we do whatever thermodynamic process we want, and then we measure again. This is the standard way of assessing transformations, right? But this is actually a problem because in the case of non-Abelian charges, because if the charges, they don't commute, when we measure the system once, which bases do we measure? I mean, if the system is in a thermal state, we just measure in the usual energy basis, that's fine. But if a system is in a non-abelian thermal state, which basis do we measure? And it turns out that there is no unique basis that can be non-invasive. Any basis we choose will always have a back action, will always destroy the system in some way. If we try to measure energy, we will mess up the squeezing. If we try to measure Sx, will mess up Sz, and so on. So there's really no way of making a compromise. Any basis we choose to measure, we will be destroying another basis. And this is directly associated. I mean, this is a very fundamental problem, right? Because it's associated to quantum coherence. And how do we actually extract these things? So we have recently shown in this paper that this can actually be overcome if you have access to multiple copies of your system. So if somehow you can prepare multiple identical copies, this can be overcome. But that is only part of a solution because, you know, in real life, we don't usually have multiple copies of our system. So that is not really, I mean, it's an interesting solution, but it's not something that solves the whole problem. So this is something we're currently working on to really how to extend this problem. And I think that the way to go is to really focus on specific platforms. Now, I showed you one example of strapped ions, and there are also other platforms where this could be implemented. And I think that this question will become much more easily addressable if we look at specific experiments. Okay, so this is pretty much what I had to say. I notice now that I'm a little bit ahead of time. I hope that's not a problem. What I wanted to conclude is that there's a lot of interesting stuff if you talk about non-commuting charges. There's a very nice interplay between quantum mechanics, information, and thermodynamics whenever you have systems where the charges don't commute. Non-commutativity is perhaps the most elegant way of viewing quantum phenomena. What really sets quantum and classical phenomena apart, you know, the fact that quantum observables are operators, that they don't commute, that's a very fundamental feature. And there's a lot to do in terms of doing thermodynamics for non-commuting charges. And essentially what we showed in this paper was just that we have a framework that is suitable for describing this kind of process in the linear response regime. Of course, that's only part of the story. There's a lot that can be done going beyond linear response, considering more complicated scenarios and so on. So these are some of the questions that we're currently working on. I would love to chat about some of them if you want. First of all, you know, how can we actually measure these? I already touched upon this. Then secondly, you know, what about current fluctuations? So you may have heard about these recent inequalities called thermodynamic uncertainty relations. They're very cute inequalities relating to current fluctuations. So they describe not the average current, but how the variance of the current, so how it fluctuates. And how will these TURs be affected by non-commutativity? I think that's a super interesting question. And finally, we're also looking for some concrete applications of squeezing and thermosqueezing. So can we make devices using this kind of phenomena and so on? So this is pretty much what I had to say. I'm open for questions and thank you very much.
Thank you very much. Now it's time for the discussions. Are there any questions or comments? Please raise your hand. Okay, Marcelo has a question.
Hi, Gabriel.
Hey.
Thank you for the nice talk. I was thinking about the generation of thermal squeezed states. You talked in the context of harmonic oscillation quantum mechanics. Is that possible to have a thermal squeezed spin state also in these Heisenberg like models?
Right, that's a very good question. Yes, the answer is yes. So if this is the kind of thing that I'm not a specialist about, but if you Google like spin squeezing, there's quite a few papers talking about spin squeezing. So essentially, it would be let's see. if you can see here. So essentially, it would be this kind of scenario, like with spin operators, but you can also squeeze them. I'm fairly sure that a state like this, which also has the SX and so on, would be some kind of spin squeeze state, but I'm not exactly sure what's the definition. But the notion of spin squeezing is also possible, because you can also have phase space for spin. I mean, you can think about this using there's this notion of spin coherent states, where you can define like a representation which is kind of similar to this one, but for spins, like in which essentially live on a sphere, and you can have spin squeezing. So that's a very good point. Maybe something I should have a look into, just extending this to squeezing. Yeah, that's interesting. Thank you.
Thank you.
Okay, also Socorro had a question. Socorro?
I don't think so.
Okay. Are there more questions here or online?
Oh, no.
Okay, so thank you very much again for the presentation.
Yeah, sorry, let me stop presenting. Yeah, thank you so much. Thank you again for the invitation. It was a pleasure. Bye.
Yeah.
We will continue according to the program.
Yes.
So 20 minutes after 3 p.m. Brazil time. So